electricity. It's hard to imagine what the world today would be like without it. Nearly everything that defines modern life is powered by electricity. Not only does it enable the obvious conveniences like lights, home appliances, and that device you're watching me on now, but it also forms the basis for things like mass communication, high-speed transportation, most forms of urban infrastructure, and much more. Even activities which in the past used to be done totally manually or through the use of animals, like agriculture, are now completely electrified, enabling previously untold levels of efficiency and profitability. Frankly, it's hard to think of an industry in modern times that doesn't in some way rely on electricity. It's very nearly the blood flowing through the veins of our civilization. Without it, we would be nothing like what we are today. So, what would happen if it were taken away? In this program, we'll be covering the sun, extreme space weather, and the threat to civilization posed by solar storms. I'm Keegan Van Hook, and this is Crossed Signals.
Nowhere to be found.
Search for signals from civilizations in space, and just one, to broadcast a message to a distant star cluster called
Nowhere to be found.
But is there anyone out there to talk to?
Our sun, a churning ball of plasma and magnetic fields, always active and ever-changing. While it at first appears to fluctuate randomly, the sun's magnetic activity follows a cycle, waxing and waning between solar minimum and maximum every 9 to 14 years, as defined by the frequency of two observable phenomena: sunspots and solar flares. In essence, a sunspot is a darkened region of the sun's surface where powerful magnetic field lines enter or exit the plasma, creating a reduced temperature. Solar flares are flashes of increased energy and brightness that emanate from solar regions full of sunspot activity. Sometimes, following a solar flare will be a coronal mass ejection, or CME, which is produced when the field lines emanating from flaring sunspots reconnect, releasing a massive amount of energy, which in turn can accelerate plasma into space. This ejected plasma, taking the form of charged electrons and protons and carrying immense magnetic fields, shoots through interplanetary space in an ever-widening field spanning the solar system, slamming anything it contacts with a powerful blast of solar radiation. If Earth is in the right position to be hit, this blast of magnetic plasma hits the planet's own magnetic field, the magnetosphere, which shields the surface from the worst of the CME's radiation and redirects most of the energy to the poles. This is actually a pretty common phenomena. It's part of what we commonly call the solar wind, and causes the famed aurora borealis and australis of the extreme north and south latitudes. This auroral effect directly reflects a surge of current in the magnetosphere. Altogether, this process can be referred to as a solar storm. These events range in scale substantially, so it's useful to have a metric to quantify them. That's why scientists use the Disturbance Storm Time Index, or DST index, which measures disturbances in Earth's magnetic field in nanoteslas. The Tesla and its small cousin the nanotesla are common units used for measuring the strength of magnetic fields. As a CME contacts the magnetosphere, it causes the nanotesla value to drop substantially. with normal being 0 nanoteslas on the DST index. Magnetic disturbances from solar wind and CMEs cause the nanotesla value to plummet into the negatives. As a benchmark, anything above negative 50 nanoteslas can be considered normal as far as our space weather environment goes. Anything from that down to negative 100 nanoteslas is a moderate storm. Anything from negative 100 to negative 250 is intense, and anything from negative 250 to negative 600 is severe.
Regardless of how powerful a solar storm is, they have essentially no bearing on life down here on the surface of the Earth. If you're a bird living in the trees, this kind of space weather has no meaning to you. As such, for us humans, geomagnetism usually bears little consequence. Part of what makes life on this planet possible is the amazing magnetosphere and its ability to act as a force shield, preventing the deadliest of the sun's radiation from reaching the ground. However, for the past century and a half or so, whenever we've seen geomagnetic storms on the intense or severe ends of the DST index, there have been anomalous and dangerous consequences. It's not us, not our bodies, nor our minds that are in danger, it's our technology. Powerful geomagnetism can have an impact on electrical infrastructure, potentially with an apocalyptic cost.
Before we get into talking about the end of the world, I want to show you one of the most fundamental aspects of electromagnetism. Before me, I have a basic magnetic induction experiment. This is a galvanometer. It's an instrument for detecting small electric currents. And connected to the galvanometer's positive and negative ends, I have this coil of copper wire. Now, when I take this magnet and run it back and forth through the coil, we can see a fluctuation of electric current measured on the galvanometer. This, in principle, is Faraday's law, otherwise known as magnetic induction, and it's the basic principle by which almost all forms of power generation work. Everything from coal plants to futuristic fusion reactors work by generating heat, usually to boil water, which spins a turbine, which in turn moves a magnet through a coil or a solenoid, generating power. While this is a simple, low-power example, it demonstrates a key principle. A moving magnetic field can have interactions with conductive materials, sparking a current. The same principle applies at any scale, including the scale of the Earth and the solar system. If it's big and powerful enough, the magnetic fields produced by a CME can have interactions with conductive materials on the Earth's surface, causing ground-induced currents, or GICs. The long distances that transmission lines, oil pipelines, and telecommunications cables cover makes them, in principle, scaled-up coils, or antennas, which can be influenced by magnetic fields and generate current in a similar fashion to our induction experiment. In human-built electric grids, this extra current, not accounted for by the network, can introduce many different power system problems, including overload of the transformers which keep the power flowing, which usually results in power outages for the area provided for by said transformers. From what little we know, it seems a storm on the order of negative 350 nanoteslas is where some of our infrastructure starts to take damage, and it gets worse as the storms do. In the right circumstances, with a powerful CME, this could happen in many different locations across continents and oceans all at the same time. With the interconnectedness of modern electric grids, a cascading failure is possible. And it's not just electrical systems which might experience damage from extreme examples of this type of space weather. Most forms of mass communication are susceptible to interference, damage, or total destruction for similar reasons. If these infrastructures are disabled thoroughly enough, effects on civilization won't stop there, but would actually become more pronounced with the second-order effects. Most all of our species' modern superpowers are dependent on a deep infrastructure of electronic technology to perform. The danger of extreme solar storms, then, is the danger of potentially losing access to most of the amenities which make modern life on Earth possible.
If you're imaginative, there are probably already a lot of worst-case scenarios running through your head. And we're going to talk much more about the consequences human civilization would face if this threat hits us in the future. But first, let's take a step back in time and explore some of the past geomagnetic events in history. Because in the long term, even extremely severe events are not rare. They've happened before, and we've seen them.
The story of how the human race came to know about solar flares is quite interesting, and not often retold. In the late morning of September 1st, 1859, a British amateur astronomer named Richard Carrington was in the midst of his customary solar observations when, to quote him,
"I was an unprepared witness to a very different affair."
Carrington was mapping the positions of sunspots by projecting the sun's disk onto a plate of distempered glass. While in the process of counting the spots, two extremely bright points of light appeared in a group to the north, as bright in the projection as the sun usually is to the naked eye. The spots traveled a short distance over the sun, then disappeared within 5 minutes, leaving Carrington shocked. What Richard Carrington had been witness to was an enormous solar flare, and he wasn't alone. Another British amateur astronomer, Richard Hodgson, had been witness to the same event, confirming the discovery of something new. What neither astronomer could know is that what they had witnessed was only a piece of a puzzle. Accompanying the flare were two equally enormous coronal mass ejections, one which had occurred before and another after, causing a long-duration solar storm measuring at an estimated DST -850 nanoteslas. The night following the observation of the solar flare, the world was globally witness to brilliant displays of red aurora borealis and australis at extremely low latitudes, as far from the poles as Cuba, sending society into a brief uproar over what it all meant.
The effect was almost bewildering and was witnessed with mingled feelings of awe and delight by thousands. Little after midnight, we were awakened by the auroral lights, so bright that one could easily read common print. Some of the party insisted that it was daylight and began the preparations of breakfast. She had become deranged from viewing the aurora borealis a short time ago. She was convinced that this spectacular auroral activity meant the world was soon to come to an end.
The aurora borealis cannot apply to the Battle of Solferino or the Peace of Villaranca. It must be connected with something in the future, war or pestilence or famine.
Likely the most notable physical impact of the September 2nd, 1859 auroral display was its effect on the telegraph system. In 1859, there were a little over 100,000 miles of telegraph line in the world, making the systems large enough that they were susceptible to ground-induced currents. The result? Much of the system overloaded, sending sparks flying at telegraph stations around the world. Perhaps the most fantastical part of all of this are the cases of telegraph operators being able to send messages to each other without the telegraph units actually being connected to any source of power. According to the accounts of operators, the geomagnetic activity was able to both neutralize and augment the telegraph batteries. This meant the batteries themselves were useless, but the telegraph units could remain on anyway, sapping electricity from the ambient air via induction. In at least one recorded instance, an operator in Portland, Maine, and another in Boston, Massachusetts, were able to have a back-and-forth exchange with disconnected telegraph machines during the 1859 storm. Ultimately, contrary to the predictions of some pundits and mystics, the world did not end in 1859. The auroral lights faded, the telegraph system began working normally again, and the human world quickly busied itself with other affairs. The greatest impact of the 1859 solar storm, which has come to be known as the Carrington event, was its impact on science. Richard Carrington himself bore witness to the great auroral display which followed his observation of the solar flare, and he was able to deduce a connection. humanity's eyes had been opened to a new paradigm. In a 2004 paper, grad students in Japan cataloged accounts of 16 incidents of red, low-latitude auroras, or seki as they're called in Japanese, documented throughout Japanese history between 1150 and 1859. While the account's details vary, it's certain at least a few of these incidents reflect Carrington-level geomagnetic events. Additionally, records from Greece, Italy, East Asia, and the Middle East suggest the same, and indicate that occurrences on the scale of the Carrington event happen roughly every 100 to 150 years. And while nothing so notable has hit the Earth since the famed Carrington event, it was not the last time the world would be made to notice the potential power of geomagnetism.
Booster ignition and liftoff of Shuttle Discovery.
Houston and Discovery, roll program.
Roger, roll, Discovery.
A sample of what could occur if one of these things hit our modern world today happened in 1989. On March 13th, aurora filled the skies as far south as Texas, and power went out for the 6 million customers of Canada's Hydro-Quebec power grid. There were substantial communication blackouts, control over polar satellites was lost, and instrumentation on the Space Shuttle Discovery malfunctioned. However, the effects were relatively minor and did not last long. Within 9 hours, power was restored to nearly all of Quebec. Communications resumed as normal, satellites regained control, and the space shuttle continued its mission. That being said, there was substantial damage to account for, amounting in $13.2 billion in melted transformers, destroyed protective equipment, and a nuclear power plant in New Jersey which had to be removed from service. The storm measured in at DST negative 589 nanoteslas, significantly less than the Carrington event, but enough to be noticed by the increasingly technological civilization of the late 20th century. It happened again in late October of 2003, to a lesser extent. Grid operators in North America noticed heating to various aspects of the electric system as a result of relatively extreme geomagnetic activity, and there was a short blackout in Sweden, but ultimately nothing much to note, as the storm was weak within the regime of extreme space weather, about DST negative 400 nanoteslas. Perhaps the most unnerving and recent example is what happened in July of 2012, when the Earth narrowly avoided being slammed by a massive CME the same size or larger than the one which caused the Carrington event. It could have caused a storm somewhere close to DST negative 1,200 nanoteslas, which would have made it the largest solar storm on record. Lucky for humanity, though, is that Earth was just slightly out of alignment on its orbit, meaning the CME passed us by without any harm. However, had the ejection been only 1 week earlier, we could have been living in a very different world by now. It was a close shave, and the inciting event that brought a lot of scientific attention to this issue.
The stories we just discussed are only a small few samples of the numerous geomagnetic events recorded throughout recent history. In fact, since the Carrington event, humans have recorded over 20 major CME-related geomagnetic storms, most all of them having very little effect on civilization, but each of them suggesting or proving the susceptibility of technology to this phenomenon. If you're old enough, you might even remember some of these events. Maybe you saw it in a story on the news, or if you were really lucky, got to see some of the out-of-place auroras yourself.
In a 2012 paper, physicist Pete Riley attempts to determine the probability of a future Carrington event. By assembling all the DST measurements of solar storms taken throughout the scientific age, Riley found that extreme storms are less common than mild ones. That seems obvious, but what's notable is that this pattern follows an almost perfect power law distribution. The frequency of a storm is, apparently, a function of its severity. By extrapolating this data model into the extremes, Riley was able to estimate the probability of a Carrington-class solar storm within the next decade. 12%.
This paper, along with historical records, confirms a startling reality. No matter what,
a future Carrington event is utterly inevitable. So, it's common for these things to happen on our world. It's happened many times before and will happen again. Luckily, we humans have spent the majority of our history in a state which has allowed us to skirt the worst possible consequences, but now it's the 2020s, and humanity is at its ultimate technological height. Power lines cover the world, and the majority of humans depend on them. Massive computerized networks for mass communication form the basis for all fashion of societal organization, from the exchange of information to the exchange of money to personal interactions. Global systems for transporting resources like food, oil, products, or really anything you can imagine are dependent on massive cargo ships and airliners, which themselves rely on immensely built-up infrastructures. High technology has become the very stuff of government, business, society, and civilization. So, if it were to suddenly be swept out from underneath us by something like a Carrington event, well, one could only imagine. If Earth were to be hit by a Carrington event today, it would be very bad news for humanity. This is the kind of thing that changes a world forever. Honestly, to paint a picture of what exactly would happen to society as a result is impossible. There are just too many factors to consider. However, a 2011 report contributed to the OECD project on future global shocks by Centra Technologies Incorporated goes into the potential consequences of a Carrington-class geomagnetic storm. Consequences from this kind of storm are described in two stages. First-order consequences, meaning infrastructure that is immediately affected, and second-order consequences, meaning the problems that arise as a result of that lost or damaged infrastructure. The Centra report identifies 8 infrastructure sectors which could be immediately affected by first-order consequences from an extreme geomagnetic storm. They are electric energy, satellite communications, wireline communications, information technology, aviation, mass transit, railroads, and pipelines. Out of all these first-order consequences, it's of course the damage to our electric grids which gives analysts the most concern. As we discussed, the onset of a severe geomagnetic storm adds excess current to electric grids. With enough excess current, transformers throughout the grid begin to overheat, and in some cases melt or explode.
Yeah. Oh shit, dude.
As a result of this, power would go out for anyone connected to the affected system. These transformers are extremely specialty hardware. Once destroyed, they typically cannot be repaired in the field, and a new unit is often required. In the best circumstances, it can take up to 12 months to get a permanent replacement. Obviously, transformers blow all the time, but because of the size and adaptability of modern grids, this rarely affects customers for long, as utility operators can redirect power through different transformers until the replacement is available. During a Carrington-class solar storm, however, we could easily see the destruction of many, perhaps even the majority, of transformers simultaneously, meaning this power redistribution option is no longer available, and where the power goes out, it stays out. What we're looking at here is the possibility of immediate, widespread power loss, with no easily predictable time when it would come back on. Assuming transformer manufacturers are able to carry out their operations at all, demand for them would be higher than ever before, and these companies would find themselves inundated with back orders. The potential for price gouging is also a major concern. How quickly power can be restored and where it gets restored first would likely become a hot political issue, if you ignore everything else that would be to follow. Assuming this is the worst case scenario and our loss of power is nearly complete on a global scale, there would be cascading second-order consequences. Almost nothing would be unaffected by this loss due to the widespread interconnectedness of modern life with electricity. Long-term power loss would disrupt transportation, communication, banking and financial systems, and government services. Factories, office buildings, web servers, and even farms utilizing industrial equipment would all come grinding to a halt. Another big thing is the loss of refrigeration, which means the spoiling of all perishable foods and medications. Thankfully, many lifeline infrastructures like water pumping stations, communications hubs, hospitals, and first responder facilities all have backup power generation, but the capacity is limited. Most all of these backups would be depleted after a month or so without mainline power. Once reserves are depleted, emergency services would become severely limited in their ability to carry out their mission, as they no longer can take calls nor adequately dispatch teams. Worse, the distribution of potable water could break down. Humans can only survive without drinking water for 3 to 4 days. With power out for months, or even years, lack of access to clean drinking water could become a critical issue. Some good news is that electronics not directly connected to the larger power grid are overall safe from damage due to geomagnetism. Your car, for example, will most likely still run, though getting more gas for it would quickly become a problem. Battery-powered devices like laptops, phones, flashlights, and cameras would all still be operable, though charging them up again would quickly become a problem. And of course, without the cellular network, internet, or other communication systems being online, many devices of this type are essentially useless anyway. While loss of ground-based communications is itself a second-order consequence related to the loss of electricity, there would be further fallout from this problem. Without mass communications, the kind of widespread cultural and societal organization we have in the modern world becomes impossible. While it's true that many of the world's largest and most prosperous nations arose before the time of efficient mass communications, all of them now rely on it. Without the ability to make a phone call, speak over radio, or transmit via satellite, the orders of a leader on one side of a country wouldn't have any way of being easily received by followers on the other. Obviously, powerful groups and individuals may be able to quickly find ways to get communications reestablished in the wake of a Carrington event. It would certainly be a priority, but there's no guarantee that the chaos and confusion of the initial breakdown is something they could overcome. That's up to fate. In circumstances such as this, when using standard communication methods like telephone, radio, or internet are out of the question, governments and institutions typically will rely on satellites to stay connected. This is most useful in locations where other forms of communication don't reach, like the deep wilderness or undeveloped countries. So one might think satellites would be our saving grace should an extreme space weather event occur, but no. As a first-order consequence of a Carrington event, damage to our orbital infrastructure would be the second biggest concern after loss of power. The storm would cause immediate and unavoidable interference to all communication systems, including contact with satellites, just as it was in 1989. Up in space, surface charge building on the satellites themselves could damage critical components, taking units offline. A Carrington-class storm could easily result in the loss of countless spacecraft, and regardless, lack of power and communication capabilities on the ground would mean losing control of any satellites that happen to survive. Second-order consequences from the loss of orbital infrastructure would not be limited to the loss of yet another communication system. It would also mean losing navigational tools like GPS and systems for monitoring the weather. This would mean countless ships lost at sea, airplanes flying off course, and extreme weather events like tornadoes and hurricanes striking without warning.
Living through something like this would be hard. The first and second order consequences we just discussed are really only the beginning of what could go wrong. While there are ways we could handle a problem like this efficiently and not collapse as a result, human beings are flawed creatures. And so while it's nice to believe that everybody would work hard together to restore the world as we know it, one must expect somewhat malevolent behaviors to take place. Greed, which leads to corruption. Bigotry, which births ills like racism and homophobia. Simple hunger for power evolving into tyranny. In an event where infrastructure is cut off, communities become suddenly isolated. Governments could only really adequately function on a local basis, with very little and very slow communication with faraway communities. In an event like this, would local municipalities have the gusto to maintain order and control without falling into these traps?
Even if governments and organizations do their part, act rationally, and do so in the name of the public good, the population at large is potentially as much a danger to societal stability as anything else. While a Carrington event lacks any sense of social class or racial boundary, affecting all of civilization at once and in the same basic ways, it would exacerbate inequalities already present within human populations. During the recovery, some may find they're able to adapt and overcome faster than others, likely in correlation with their status prior to the event. Additionally, it's possible, perhaps even probable, that a major portion of any given population would come to distrust those in control of the infrastructure, elected politicians, and industry leaders. Poor communication from leadership or a lack of understanding and care for the needs of the population could lead to the perception that new authority is needed. And once you're there, social unrest is never far away.
Pretty much every apocalypse movie ever fills in the gaps of what I'm not saying here. An event like this could potentially change the world forever in profound ways we can't even begin to speculate on with any accuracy. Not everything I've talked about here would happen everywhere all at once, and I'm definitely talking about a worst possible case. But what I hope I've painted for you is a realistic picture of the kind of danger we face as a civilization. With events like this happening on average every 100 to 150 years, with a decade-by-decade probability of 12%, we're overdue to be hit by a Carrington-class geomagnetic storm. If you're convinced, this can all be a very hard pill to swallow. To know that an unparalleled catastrophe is imminently on its way is terrifying knowledge to know. But with that knowledge comes the benefit of real power. And finally, I have good news. We humans possess a lot of knowledge about this problem, and consequently possess all the powers necessary to protect ourselves. The question is if we'll care to do so. So, how do we prepare ourselves for this? We'll cover this question in 3 phases: prevention and forewarning, infrastructural hardening, and future-proofing.
Humanity does not currently have any way to predict future solar storms. Pete Riley was able to determine the probability of these events based on a backlog of data, but this data suggests no discernible pattern in the timing of extreme events. At best, we can monitor the solar cycle, with the understanding that there is higher risk during the period of solar maximum. But for all intents and purposes, there is no way to predict the coming of a coronal mass ejection, and therefore no way to predict the onset of a geomagnetic event in the long term. The near miss of 2012 was discovered using NASA's Stereo A spacecraft, a solar observatory, which was luckily in position to take readings and hardened enough to survive the onslaught of solar radiation. This satellite was able to tell us about the speed, strength, and most importantly, the trajectory of the ejection. In order to keep up with our local space weather, modern humanity needs to establish a robust space weather monitoring system, consisting of multiple observatories. This would guarantee us several hours to batten down the hatches. Currently, there are several spacecraft giving us partial capabilities in this area. These spacecraft are all capable of performing the duties of a forewarning system, but they don't cover the solar system entirely, and don't give warnings as early as is ideal. Not all of these missions are related to each other. Some of them come from many different places around the world, and so communication is not perfect. Currently, space weather forewarning services are handled through a combination of intergovernmental cooperation and private-public partnerships. However, there is no formal mechanism for risk management on an international scale. Most of the world's nations have no national-scale mitigation strategy to deal with the news of an incoming storm once it arrives. In general, this is a problem which is not given as much stock from governments as other forms of natural disaster, despite the certain risk. That being said, there are things being done. The International Space Environment Service, or ISS, currently serves as the closest thing the world has to a real, planetary defense against the threat of geomagnetic storms. While ISIS exists as a loose net of independent parts, including NASA, NOAA, and the ESA, among other organizations, its framework does mean that any early detection of an extreme storm would be available to the whole world.
So we do have monitoring and forewarning systems in place, and despite them being spotty, they do provide us with a certain element of protection. If warning of a geomagnetic storm came down from above, grid operators could take precautions, such as decreasing the load on the electric grid, essentially turning it off and waiting it out. While this could still produce blackouts lasting a number of hours or perhaps a day or two, the long-term damage to infrastructure could be avoided. But that's only with warning, which is not guaranteed and doesn't cover satellite infrastructure. The absolute best thing we could do to protect ourselves would be to fortify our infrastructure against the negative effects of solar storms, so that even if one hits without warning, we're taken care of. But this is where things start to get expensive and politically challenging.
There are several steps which can be taken to harden our electric grids against geomagnetic storms. Namely, special emergency capacitors can be installed on the lines ahead of transformers, so that when extra current is induced in the system by geomagnetism, the capacitors do the job of absorbing the difference, instead of the more sensitive and critical transformers. Additionally, GIC monitors can be placed on the transformers, which ensure that currents remain at stable levels. For satellites, components can be hardened against electric surface charging in a similar fashion. However, the biggest problem with all these solutions is their cost. For electric grids, these extra components are not cheap, and in many cases require further overhauls to be made before they can be employed. As for satellites and spacecraft, any additional weight can mean the difference between a mission being feasible or unaffordable. After the solar storm of 1989, wherein Quebec experienced massive power loss, the Canadian government invested $1.2 billion into protective equipment for the Hydro-Quebec grid. That's a pretty big figure, which can easily cause politicians or industry leaders to balk, but when compared to the $6 billion spent by Quebec on the damage caused by the 1989 storm, it's clear that investment ahead of a disaster is well worth it.
Unfortunately, outside of Canada, very little has been done directly in the name of hardening our infrastructure against the threat of geomagnetic storms. Public awareness of this issue is low in most countries, and before it happens to you directly, it can be a very abstract idea. The modern world at large has never experienced consequences from any sort of cosmic phenomena, so even the very real threats like solar storms are out of place, out of mind. Therefore, it doesn't seem to be in the best interest of leaders to raise the issue, perhaps for fear of looking like a doomsday prepper, and the whole matter is almost never brought up as an issue of public interest. The best hope humanity has of shielding itself from this problem, then, is to invest in technologies and mitigation efforts that kill two birds with one stone. Luckily, there are things which are being done right now that decrease the geomagnetic risk factors for our infrastructure while also addressing more down-to-earth interests.
One hopeful development is the increasing trend of developed nations towards smart grids, which entails several shifts in the model of how electricity is generated and distributed. Historically, power grids have been centralized, with one major source of failure: the power plants. In a Carrington event, if the transformers along the transmission lines between a power plant and power consumers are disabled, power is out. In a smart grid, power generation is intentionally distributed among a diverse set of techniques, usually renewables like solar, wind, and hydro, scattered broadly across the geography. This decreases the odds that all forms of power generation are permanently cut off from consumers. And smart meters on homes and buildings, which report real-time information to an advanced network, are able to detect when a problem arises in their area, allowing the whole grid to adapt, decreasing the chances of cascade failure. Unlike other techniques to harden against solar storms, smart grids are not as difficult to convince politicians and industry leaders to invest in because they introduce economic and environmental benefits whether or not a disaster occurs. Smart grids are generally a more renewable, more efficient, and more adaptable option for communities to save money both for power producers and consumers. Steadily, the smart grid concept is on the uptake, and investment is increasing across the world. As we slowly move further in this direction, the risk factors that come with an extreme solar storm decrease.
I wish I could tell you more about what humanity is doing to protect itself, but that's really just about it. We certainly know a lot about what we should be doing, but outside of the slow adoption of smart grids, there's very little interest in this problem as compared to other similarly existential problems. There are a lot of problems here on Earth, and it's always tempting for folks to say that we should focus on what's right in front of us before we worry about the development of our space capabilities. We have hunger, oppression, and global warming all right here in our habitat. It's very tempting to say that we should focus on these problems with our habitat before thinking beyond it. But that fails to realize that our habitat is not just this planet. It's the solar system, the whole galaxy, and the universe. Things beyond our world can have an impact on us, and in some cases, like this one, an extreme impact. A Carrington event is coming. It's only a matter of time. What the exact fallout of that will be, I do not know, but right now, it very much appears that we may have to learn that lesson the hard way. Thanks for watching, and good night.